Today I want to discuss the ocean energy. In this lecture I want to discuss the introduction to the ocean energy, open and closed cycle conversion, practical considerations about the OTEC, advantage and disadvantages of the OTEC, related technologies of OTEC, social, economic and environmental aspects of the OTEC, and the applications of the OTEC. Now come to the introduction of the ocean energy. The ocean is the world's largest solar collector. In tropical seas, the temperature differences of about 20 degrees centigrade occur between the warm near surface water and the cold deep water at 500 to 1000 meter depth. Heat engines can operate between the thermal sources and the sinks, which has relatively small temperature difference, but their intrinsic efficiency is small due to the laws and the practicalities of the thermodynamics. Ocean thermal energy conversion is the extraction and conversion of this thermal energy into the useful work for the electricity generation. The OTEC relies on the principle exploited in most forms of the electricity generation that a source of heat and a source of cold can be used to drive an engine. In the case of OTEC, the source of heat is the surface of a tropical or the subtropical sea, while the source of cold is the deep sea. Given the sufficient scale of efficient equipment, the electricity power generation could be sustained day and night at approximately 200 kilowatt energy per kilometer square in areas of the tropical sea. Such power equals about the 0.07% of the absorbed solar radiation input to that area. The possibility of extracting energy from the sea in this way was recognized in the latter half of the 19th century, and the first practical system was proposed by the French inventor D'Arsenal in 1881. D'Arsenal systems employed a closed cycle ammonia turbine, and it was finally demonstrated in 1979 in a small pilot project of Hawaii. However, a different open cycle system was tested during the 1930s by another Frenchman, Georges Claude. Claude's system proves the theory on which it was based, but was not successful commercially. Work was not received on this system until the late in the 20th century. Some R&D efforts was resourced from the France pre-1970s, and then from the USA, Japan and the Taiwan in the 1980s, and with the continuing very moderate activity since then. The tropical oceans and the seas have the surface water temperatures of between 24 degrees centigrade and 33 degrees centigrade. Below 500 meters, the temperature will drop to between the 9 degrees centigrade and the 5 degrees centigrade. This provides a maximum exploitable temperature difference of 28 degrees centigrade. In practice, the temperature difference is likely to be closer to 20 degrees centigrade, providing a theoretical energy conversion efficiency of 6.7%. When account is taken of the need to pump cold water up from the depth, efficiency falls to 2 to 3%. For OTEC, the hot source is the tropical surface water at 25 degrees centigrade, and the cold sink is water from the deep ocean at 5 degrees centigrade. This cold saline water has to be pumped up to the surface level to become a colder thermal sink for the heat engine, for which the considerable pumping power is required. In practice, the pumping is at a rate of about 6 meter cube per second of water per the megawatt energy of the electricity generated, which may require up to the 50% of the generated power. Such systems require the large pumps, large diameter pipes, and the large heat exchangers, all of which are very much expensive. Though the cool water may be available at 500 meter, in practice the depth of 1000 meter is normally considered necessary. If this is to be made accessible from land, a very long cold water pipe will be required to pump the deep water to the plant. To tackle the technical limitations, the OTEC designers use the methods of established industries for the energy recovery. Just example from large flows of heated discharge from the metal refining, power stations, and the food industries. This pipe will need to be 2000 meter or more in length, and if the care is not taken, the cold water will become warmed before it reaches to the. The alternative is to build an OTEC plant on a floating platform from which the cold water pipe stretched vertically downwards. Even with this arrangement, the cold water pipe will need to be 1000 meter long. In order to generate the 1 megawatt of electricity, an OTEC plant requires 4 meter cube per second of warm seawater and 2 meter cube per second of the cold seawater. This will require a cold water pipe of around 1 meter in diameter to supply a 100 megawatt plant, the largest size considered practical. The discharge of mixed hot and cold water from a plant of this size would be equivalent to that of the Colorado River in USA discharging into the Pacific Ocean. Such massive quantities of water could have significant environmental impact. The attractiveness of the OTEC from the successful plant is the effectively limitless energy of the hotter surface water in relation to the colder deep water, and its potential for constant baseload electricity generation, such that the plant has the potential for large capacity factor approaching 100%. However, the OTEC faces the three fundamental limitations. First is the pumping. Heat engines depends on the energy passing down a temperature gradient from a hotter source to a colder sink, such that in steam from approximately 150 degrees centigrade to the ambient temperature approximately 25 degrees centigrade. Second limitation is the small efficiency. In practice, the temperature difference available to operate the heat engine is small, and so the efficiency of even a perfect engine is very small at greater than 5%. Third one is the remote location. Sites with the VOTEC potential are either at tropical coastlines or offshore using the large floating installations. Such sites are usually far from the habitations, having the capacity to utilize the VOTEC output. To tackle the technical limitations, the VOTEC designers use the methods to establish the industries for energy recovery, such that from large flows of the heated discharge from the metal refining, power stations, and the food industries. In addition, the VOTEC can combine with other applications using the deep water. The general term for such development is deep ocean water applications, that is called DOA. It is probable that the only joint VOTEC or the DOA schemes are ever likely to be commercially successful. The setting up of an VOTEC plant, either offshore or onshore, represents one of the key decisions for any proposed project. The other key decision is the type of the cycle to use. There are two principal options, an open cycle plant and a closed cycle plant. The hybrids of the two have also been proposed. The figure is shown as the open cycle VOTEC plant, which I will describe elaborately in the next slide. And the second one is in the closed cycle VOTEC plant. A closed cycle VOTEC plant employs a thermodynamic fluid such as ammonia or a refrigerant like freon. This is contained in a completely closed system including the plant turbine. The figure shows the closed cycle VOTEC plant. Hot surface seawater is used to evaporate the fluid by the evaporator, and the vapor is then exploited to drive the turbine. This is the turbine. The vapor from the turbine exhaust is condensed by the condenser using the cold deep ocean water and return to the beginning of the cycle, where it can be reheated by the evaporator. This is the flow diagram of the closed cycle system. The warm seawater and the cold seawater are pumped to the evaporator and the condenser. The cold working fluid is pumped to the evaporator. The evaporator uses the warm seawater to vaporize the working fluid. The vapor then rotates the turbine, thereby generating the electricity. The vapor then enters to the condenser, where the cold seawater cools it to a fluid, and then the fluid is again returned to the pump and the cycle is repeated again. Now the open cycle VOTEC. In an open cycle VOTEC system, the seawater itself is used to provide the thermodynamic fluid. The warm seawater is expanded rapidly in a partially evacuated chamber, where some of it flashes to the steam. This steam is then used to drive a steam turbine. This is the steam turbine. From the exhaust, the turbine, the vapor is condensed using the cold seawater. The vapor produced by flashing warm seawater is at a relatively low pressure, so it requires a very large turbine to operate effectively. Practical limitations means that the largest open cycle turbine that can be built today is around 2.5 megawatt, much smaller than for a closed cycle system. One of the major advantages of the open cycle system is that the water condensed from the turbine exhaust is fresh, not salt water, and so the plant can also serve as a source of the drinking water as well as the electricity. A 50 kilowatt closed cycle OTEC plant was built in Hawaii in 1979 and operated for a few months. A consortium of the Japanese companies has also operated a 100 kilowatt closed cycle OTEC plant in Nauru. Again, this plant operated for only a few months to prove the concept. Neither was large enough to be commercially viable. Indeed, the closed cycle OTEC is unlikely to be commercially viable in sizes of less than 40 megawatt. A 210 kilowatt open cycle OTEC pilot plant operated in Hawaii between the 1993 and the 1998. In a hybrid OTEC plant, the warm seawater is flashed to produce the steam which is shown in the figure. This is the flash chamber. And this steam is then employed as the heat source for a closed cycle system. This is the closed cycle system, this is the open cycle system. So for this is made as the hybrid OTEC plant. This system is more complex than either of the other cycles, but it marries the concept of the compact closed cycle system with the ability to produce the drinking water. Now come to the practical considerations about the OTEC. First is the heat exchangers. So the figure shows the outline design of a cell and tube heat exchanger suitable for closed circuit OTEC. But for the 1 megawatt thermal output at the small temperature differences, this would require the several thousand internal tubes. These are the internal tubes with a total surface area is greater than 2000 meter square. Thus, the OTEC heat exchangers must be relatively large to provide the sufficient area for the heat transfer at low temperature difference and are therefore expensive, perhaps 50% of the total cost. Moreover, the calculation of ideal output power is assumes perfect heat transfer between the external ocean water and the internal working fluid. This is unrealistic, especially owing to the biofouling outside and inside the pipes. Therefore, the development of the OTEC includes improvements in existing heat exchangers to increase the thermal resistance between the water and the working fluid. The aim is for more efficient and therefore smaller heat exchangers which with less metal may give the significant cost reduction. Second consideration is the biofouling and the corrosion. The inside especially of the pipes become encrusted by marine organisms which increase the thermal resistance, so reducing efficiency. Such biofouling is one of the major problems in WOTEC design, since increasing the surface area available for heat transfer also increases the opportunity for organisms to attach themselves. Among the methods tried to keep this fouling under control are mechanical cleaning by continual circulation of the close-fitting balls and chemical cleaning by additives to the water. In addition, the serious corrosion can occur with the metal structures, including the inner heat transfer tubing of the heat exchanger. Third one is the pumping requirements. Work is required to move the large quantities of hot and cold water around the system against the friction. This power is supplied from the gross power output, so reducing the ideal power output. Although the cold water pipe can be built large enough to avoid the significant friction, because the head loss varies as diameter, friction loss may become appreciable within the connections and in the smaller pipes inside the heat exchangers. Biofouling within the heat exchanger tubes increases friction with roughness and decreases the tube diameter, making the situation worse. Consequently, over 50% of the pumping power may be lost due to fluid. Fourth one is the land-based. The land-based, self-based and the floating type considerations should be maintained. The land-based and the near-shore facilities offer three main advantages over those located in the deep water. The plants constructed on or near land do not require sophisticated mooring. Laying the power cables or the more extensive maintenance associated with the open ocean environments. Then they can be installed in sheltered areas so that they are relatively safe from the storms and the heavy seas. Electricity, desalinated water and the cold nutrient-rich seawater could be transmitted from near-shore facilities via the textile bridges or the causeways. In addition, the land-based or the near-shore sites allow the plants to operate with the related industries such as maricultural or those that require the desalinated water. Favored locations include those with the narrow shelves, that is volcanic islands, steep 15 to 20 degrees offshore slopes and relatively smooth sea floors. These sites minimize the length of the intake pipe. A land-based plant could be built well inland from the shore, offering more protection from the storms, or on the beach where the pipes would be very shorter. In either case, easy access for construction and operation helps the lower cost. Land-based or near-shore sites can also support the mariculture or the chilled water agriculture. Tanks or the lagoons built on shore allow the workers to monitor and control the miniature marine environments. Mariculture products can be delivered to market via standard transport. One disadvantage of the land-based facilities arises from the turbulent wave action in the surf zone. The WOTEC discharge pipes should be placed in protective trenches to prevent the subjecting them to extreme stress during the storms and the prolonged periods of the heavy seas. Also, the mixed discharge of the cold and warm seawater may need to be carried several hundred meters offshore. to reach the proper depth before it is released, requiring the additional expense in the construction and maintenance. One way that the VOTEC systems can avoid some of the problems and expenses of the operating in a surf zone is by building them just offshore in waters ranging from 10 to 30 meters deep. This type of plant would use the shorter intake and discharge pipes, which would avoid the dangers of the turbulent surfing. The plant itself, however, would require protection from the marine environment, such as breakwaters and the erosion-resistant foundations, and the plant output would need to be transmitted to shore. Now the self-based, to avoid the turbulent surf zone as well as to move closer to the cold water resource, VOTEC plants can be mounted to the continental shelf at depths up to 100 meters. A self-mounted plant could be towed to the site and affixed to the sea bottom. This type of construction is already used for offshore whale rigs. The complexities of the operating and VOTEC plant in deeper water may make them more expensive than the land-based approaches. Problems include the stress of open ocean conditions and more difficult product delivery. Addressing strong ocean currents and large waves adds engineering and construction expense. Platforms require extensive piling to maintain a stable base. Power delivery can require long underwater cables to reach land. For these reasons, self-mounted plants are less attractive. Now come to the third practical considerations is the floating. Floating VOTEC facilities operate the offshore, although potentially optimal for the large systems. Floating facilities present the several difficulties. The difficulty of mooring plants is in very deep water complicates power delivery. Cables attached to floating platforms are more susceptible to damage, especially during the storms. Cables at depth greater than 1000 meters are difficult to maintain and repair. The riser cables which connect the seabed and the plant need to be constructed to resist the entanglement. As with the self-mounted plants, the floating plants need a stable base for the continuous operation. Major storms and heavy seas can break the vertically suspended cold water pipe and interrupt warm water intake as well. To help prevent these problems, pipes can be made of flexible polyethylene attached to the bottom of the platform and gimbaled with the joints or the collars. Pipes may need to be uncoupled from the plant to prevent the storm damage. As an alternative to a warm water pipe, the surface water can be drawn directly into the platform. However, it is necessary to prevent the intake flow from being damaged or interrupted during the violent motions caused by the heavy seas. Connecting a floating plant to power delivery cables requires the plant to maintain the relatively stationary. Mooring is an acceptable method, but current mooring technology is limited to depths of about 1000 meters. Even at the shallower depth, the cost of the mooring may be prohibitive. Construction of the cold water pipe. The suspended cold water pipe is subject to many forces, including those due to the drag by the currents, vortex shedding, motion of bows and the platforms, and the dead weight of the pipe itself. In addition, there are substantial difficulties involved in assembling and positioning the pipe. Some engineers favor bringing out a prefabricated pipe and slowly sinking it into the place. However, transporting an object several meters in diameter and perhaps a kilometer long is very difficult. Premature failure of the cold water pipe from the storm damage has caused the failure of the several demonstration projects. The power connections. High voltage large power submarine cables are standard components of the electrical power transmission system. Cables to 500 km in length are practice cable with the power loss about 0.05% per kilometer for the AC and 0.01% per kilometer for the DC. There is now considerable experience for the underwater connections in the power grid networks and for the offshore wind power. Large OTEC plants located far from the energy demand could in principle use the electricity to produce a chemical store of energy. Now come to the advantages and disadvantages of the OTEC. The advantages are the steady output, uses the conventional engineering hardware of turbines, pipes and the heat exchangers, limited only by the size of the machinery. It is quite seemingly small environmental impact, may be linked with the associated deep ocean water application. Now come to the disadvantages. Extremely small hydrodynamic efficiency, hence the large installations needed for the meaningful power output, hence it is very expensive. Surface and near surface equipment exposed to the cyclones and the storm waves. Biofouling within the pipes restricts the flow, increases the pumping pressure and reduces the heat exchanger efficiency, thereby decreasing the overall efficiency. The biofouling can be overcome with the burst of the chemical herbicide but have unwanted environmental impact. Undersea and the above sea pipes are difficult to insulate at large scale, hence the unwanted heat entry and loss of power potential. International cooperation is limited to only a few interested countries. Now the related technologies of the OTEC. The OTEC is one of the several possible deep ocean water applications that is called DAWAs, associated with the pumping sea water from the depths of at least 100 meters. This is the deep ocean water application that is called DAWA. Others are listed below. The marine farming, sea water from the depths below about 500 meters is rich in nutrients and these may be pumped to the surface as from an OTEC plant. This encourages the growth of the algae that is called the phytoplankton, which feed other marine features higher up the food chain and so provide a basis for the commercial fish farming. Second is called the cooling. The deep cool water pumped to the surface may be used to cool buildings, tropical horticultural greenhouses, or the engineering plant as in chemical refineries. Desalination or the fresh water. The flash evaporation of the upper surface seawater onto the condensers cooled by deep water produces the distilled fresh water for drinking, horticulture, etc. This process may be integrated with the solar distillation. The OTEC and open cycle Rankine engine inputs water vapor and the outputs a mist of partly condensed water. This output is in effect distilled water and may be used for the potable and the agricultural water. The carbon dioxide injection. The aim is to absorb the carbon dioxide emitted from the large-scale fossil fuel combustion by absorption in seawater and then pumping this to depth. This is one type of carbon capture and storage that is called CCS. It is almost the reverse of the technology for the OTEC cold water pipe and potentially would be on a very large scale. If combined with the OTEC, the evaporator output would absorb the carbon dioxide and then be pumped down for the discharge at depth. However, there are significant unresolved issues with such suggestions, including the environmental impact on the biota at depth, cost, and the long-term scalability or the long-term stability of the capture. The floating industrial complexes concepts exist to make the large scale of the OTEC and the DAWA with the industry on very large floating rafts of kilometer scale. Now come to the social, economic and the environmental aspects of the OTEC. The social aspects: the resource for the OTEC is effectively limited to the coast or islands in the tropics. However, most such places are in poorer countries which lack the funds to bear the risks and burden associated with the novel capital-intensive technologies, with a few notable exceptions such as the Hawaii, Florida, and the Brazil. In such places, the social impacts of the OTEC plant would be similar to operating an offshore well rig or an onshore power station. Now come to the economic aspects. The economics of the OTEC are dominated by the high projected capital cost arising from the large size of the OTEC components and the demands imposed by offshore environments on equipment survival and power production logistics. This as well as the relatively small power outputs result in analysis based on the levelized cost of the electricity generation and consistently find the OTEC projects have too small a cost benefit ratio to be economically worthwhile. Even though the cost effectiveness gap between the OTEC and the most expensive fossil fuel power generation technologies has steadily declined since 2000, OTEC market penetration has not yet succeeded. Because of a lack of experimental and operational data in running the OTEC system, however, taking the advantage of this purported economy of the scale presents a large financial and engineering risks, with the capital outlays as high as the $300 million for power outputs of the order of 10 megawatt. Hence, it remains likely that any meaningful demonstration of the scalable OTEC systems will be accomplished only with the strong commitment of the public funds. Now the environmental aspects. The main environmental impacts of the OTEC and DAWA technologies relate to the following: leakage and likely pollution from the engineering plants, especially of the working fluids and the anti-fouling chemicals, large volumes of the pumped marine water, mixing of deep nutrient rich, that is called nitrate, phosphate and silicate water with the upper solar irradiated water, operation of the engineering plant usually in pristine marine locations. A dominant harmful threat is the local onshore, nearshore and the offshore pollution from the leaks of the working fluids. The electricity production is the first application of the OTEC. The ocean thermal energy conversion uses the ocean thermal gradient between the cooler deep and warmer shallow or the surface sea waters to run a heat engine and produce the useful work, usually in the form of electricity. OTEC is one of the continuously available renewable energy resources that could contribute to the base load power supply. Up to the 88,000 terawatt hour per year of power could be generated from the OTEC without affecting the ocean's thermal structure. Second application is the desalination. Desalinated water can be produced in open or hybrid cycle plants using the surface condensers to turn the evaporated seawater into the potable water. System analysis indicates that the 2 megawatt plant could produce about 4,300 cubic meters of the desalinated water each day. Another system patented by the Richard Bailey creates the condensate water by regulating the deep ocean water flow through the surface condensers, correlating with the fluctuating dew point temperatures. This condensation system uses no incremental energy and has no moving parts. On March 22, 2015, the Saga University opened a flash-type desalination demonstration facility on the Kumejima. This satellite of their Institute of the Ocean Energy uses the post-OTEC deep seawater from the Okinawa OTEC demonstration facility and the raw surface seawater to produce the desalinated water. Air is extracted from the closed system with a vacuum. When the raw seawater is pumped into the flash chamber, it boils, allowing the pure steam to rise and the salt and remaining the seawater to be removed. The steam is returned to the liquid in an heat exchanger with the cold post-OTEC deep seawater. The desalinated water can be used in hydrogen production or drinking water. The Nela plant, established in 1993, produced an average of 7,000 gallons of the fresh water per day. The Koyo USA was established in 2002 to capitalize on this new economic opportunity. The Koyo bottles and the water produced by the Nela plant in Hawaii. With the capacity to produce 1 million bottles of water per every day, Koyo is now the Hawaii's biggest exporter with the $140 million in sales. Another application in the air conditioning, the 41 degree Fahrenheit, that is called 5 degree centigrade cold sea water made available by an OTEC system creates an opportunity to provide the large amounts of cooling to industries and homes near the plant. The water can be used in chilled water coils to provide the air conditioning for buildings. It is estimated that a pipe of 1 foot in diameter can deliver the 4,700 gallons of water per minute. The water at 43 degree Fahrenheit, approximately 6 degrees centigrade, could provide more than enough air conditioning for a large building. Operating 8,000 hours per year in lieu of electrical conditioning, selling for 5 to 10 per kilowatt hour, it could save the $2 lakh to the $4 lakh in energy bills annually. The Intercontinental Resort and the Thalasso Spa on the island of Bora Bora uses and the SWAC system to the air condition its. The system passes seawater through a heat exchanger where it cools fresh water in a closed loop system. This fresh water is then pumped to the building and directly cools the air. In 2010, the Copenhagen Energy opened a district cooling plant in the Copenhagen, Denmark. The plant delivers cold seawater to commercial and industrial buildings and has reduced the electricity consumption by 80%. Ocean Thermal Energy Corporation, that is called OTE, has designed the 9,800 ton HDC system for a vacation resort in the Bahamas. Another application is the hydrogen production. Hydrogen can be produced via the electrolysis using the OTEC electricity. Generated steam with the electrolytic compounds added to improve the efficiency is a relatively pure medium for the hydrogen production. The OTEC can be scaled to generate the large quantities of hydrogen. The main challenge is the cost relative to the other energy sources. The chilled soil agriculture is the another application. The OTEC technology supports the chilled soil agriculture. When the cold seawater flows through the underground pipes, it chills the surrounding soil. The temperature difference between the roots in the cool soil and leaves in the warm air allows the plants that involved in the temperature climates to be grown in the subtropics. Dr. John P. Craven and the Dr. Jack Davidson and the Richard Bailey patented this process and demonstrated it at a research facility at the Natural Energy Laboratory of Hawaii. The research facility demonstrated that the more than 100 different crops can be grown using this system. Many normally could not survive in Hawaii or at the Koiol. Japan has also been reaching agricultural uses of the deep sea water since 2000 at the Okiwa Deep Sea Water Research Institute on the Kyum Island. The Kyum Island facilities use the regular water cooled by deep sea water in a heat exchanger run through the pipes in the ground to cool soil. Their techniques have developed an important resource for the island community as they now produce the spinach, a winter vegetable commercially year-round. An expansion of the deep sea water agriculture facility was completed by the Kumenjima town next to the OTEC demonstration facility in 2014. The new facility is for researching the economic practicality of the chilled soil agriculture on a large scale. Aquaculture is the best known byproduct because it reduces the financial and energy cost of the pumping large volumes of water from the deep ocean. Deep ocean water contains the high concentrations of the essential nutrients that are depleted in surface waters due to the biological consumption. This artificial upwelling mimics the natural upwellings that are responsible for fertilizing and supporting the world's largest marine ecosystems and the largest densities of the life on the planet. Cold water delicacies such as salmon and the lobster thrive in this nutrient-rich deep sea water. Microalgae such as spirulina, a health food supplement, also can be created. Deep ocean water can be combined with the surface water to deliver the water at an optimal temperature. Non-native species such as salmon, lobster, abalone, trout, oysters and clams can be raised in the pools supplied by the OTEC pumped water. This extends the variety of fresh seafood products available for nearby markets. Such low-cost refrigeration can be used to maintain the quality of the harvested fish, which deteriorate quickly in warm tropical regions. The mineral extraction. The ocean contains 57 trace elements in salts and other forms and dissolves in solution. In the past, most economic analysis concluded that the mining the ocean for the trace elements would be unprofitable, in part because of the energy required to pump the water. Mining generally targets the minerals and occur in high concentrations and can be extracted easily, such as the magnesium. With OTEC plants supplying water, the only cost is for the extraction. The Japanese investigated the possibility of extracting the uranium and found the developments in other technologies were improving aspects. And another application is the climate control. Ocean thermal gradient can be used to enhance the rainfall and moderate the high ambient summer temperatures in tropics to benefit the enormously the mankind and the flora and fauna. When the sea surface temperatures are relatively high on an area, the lower atmospheric pressure area is formed compared to the atmospheric pressure prevailing on the nearby land mass, including the winds from the land mass towards the ocean. Oceanward winds are dry and warm, which would not contribute to good rainfall on the land mass compared to the landward moist winds. For adequate rainfall and comfortable summer ambient temperatures on the landmass, it is preferred to have the landward moist winds from the ocean. Creating high pressure zones by artificial upwelling on the sea area selectively can also be used to deflect or guide the normal monsoon global winds towards the landmass. Artificial upwelling or the nutrient-rich deep sea water to the surface also enhances the fisheries growth in areas with the tropical and temperature weather. It would also lead to enhanced the carbon sequestration by the oceans from improved algae growth and the mass gain by the glaciers from the extra snowfall, mitigating the sea levels rise or global warming process. Tropical cyclones also do not pass through the high pressure zones as they intensify by gaining the energy from the warm surface waters of the sea. The cold deep sea water is pumped to the sea surface area to suppress the sea surface temperatures by artificial means using electricity produced by mega scale floating wind turbine plants on the deep sea. The lower sea water surface temperature would enhance the local ambient pressure so that the atmospheric landward winds are. For upwelling the cold sea water, a stationary hydraulically driven propeller is located on the deep sea floor at 500 to 1000 meter depth with a flexible draft tube extending up to the sea surface. The draft tube is anchored to the sea bed at its bottom side and top side to the floating pontoons at the sea surface. The flexible draft tube would not collapse as its inside pressure is more compared to the outside pressure when the colder water is pumped to the sea surface. The Middle East, Northeast America, Africa, Indian subcontinent and Australia can get the relief from the hot and dry weather in summer season, also prone to erratic rainfall, by pumping the deep sea water to the sea surface from the Persian Gulf, Red Sea, Indian Ocean and the Pacific Ocean respectively. So these are the references from where I make this lecture. You should go through these references.